Today on My Climate Journey, our guest is Dr. Peter Fiske, Executive Director at the National Alliance for Water Innovation, or NAWI. NAWI is a collection of 19 universities, 4 national labs, and 190 plus U.S. water companies committed to developing new technologies to enable distributed desalination and water reuse. They are a 5-year, $110 million research program supported by the U.S. Department of Energy in partnership with the California Department of Water Resources and the California State Water Resources Control Board. They are headquartered at Lawrence Berkeley National Lab in Northern California. Peter joined Berkeley Lab in 2017. Prior to that, he was the Chief Executive Officer at Pax Water Technologies from 2008 until January 2017, when it was acquired by UGSI Incorporated. Peter holds a PhD in geochemistry and material science from Stanford and an MBA from the UC Berkeley Haas School of Business. Our conversation today starts with a deep dive into desalination before broadening out into Peter's vision for our water system overall. Thank you to former pod guest Tom Ferguson at Burnt Island Ventures for connecting us with Peter. I've been wanting to learn about desal, and Peter helped me gain a much better understanding of that and so much more. But before we start, I'm Cody Sims.
I'm Yin Lu.
And I'm Jason Jacobs. And welcome to My Climate Journey.
This show is a growing body of knowledge focused on climate change and potential solutions.
In this podcast, we traverse disciplines, industries, and opinions to better understand and make sense of the formidable problem of climate change and all the ways people like you and I can help. Peter, welcome to the show.
Thank you, Cody. Good to see you.
So as you so aptly pointed out in our little pregame chat, we as MCJ have done over 500 episodes of the show, and that's a lot of journeys to have been on from a climate perspective.
A lot of journeys. You surely are somewhere by now.
And one thing that we've learned for sure is there's no magic bullet when it comes to climate change. But another thing we've learned is that water in particular will be one of the primary symptoms through which all of us experience climate change. And so I'm really excited to have you on today and learn from you about all of the work you're doing around water and around what ongoing access to water will look like for all of us.
Water is the delivery vehicle for the effects of climate change. That was what one of the panelists of the IPCC said about 10 years ago. And it's absolutely the case. We are seeing is the temperatures change. What you approximately see is major effects to water, how it's delivered by nature, how it's managed by man. Drier areas get drier, wetter areas get wetter, storms get more violent. So everything is turned up to 11 when we talk about water.
And I'd love for you to introduce a bit about the work you do at NAWI, which is the National Alliance for Water Innovation, where you serve as executive director. Maybe share a bit more about the scope of that project.
Well, NAWI is a 5-year research program funded by the U.S. Department of Energy in collaboration with the California Department of Water Resources and several other partners. The goal was to radically improve the performance of desalination and water reuse. And it's normal when people hear the word desalination, they think, oh, a big water factory by the coast. And most people, when they think of desalination, think of ocean desalination. It turns out, Cody, desalination is actually a very handy tool in a more general water reuse toolbox. So you can use desalination, which is literally the process of pulling salt ions out of water. You can use that to take water that's wastewater from industrial and municipal applications. You can take water that's not seawater, but salty groundwater called brackish groundwater. You can use desalination to pull out those salty ions and return the water to high quality and usability. And so at NAWI, we fund advanced research teams, usually combinations of industry, academia, and national lab scientists who are pushing the frontier of desalination technologies and systems. And we are 4 years into our program. We have got another 1 year left on our first 5-year mission. But like Star Trek, it sounds like the Department of Energy is going to give us another 5 years. So we will have a continued journey of the Starship NAWI and hope to further advance desalination and water reuse.
To boldly go where no man has gone before.
Exactly.
And the labs that you work with are Lawrence Berkeley, Oak Ridge, NREL, and the National Energy Technology Laboratory. Is that correct?
That's correct. As well as we have research performers in most of the other national labs. And actually today we have more than 150 research organizations, universities, national labs, private laboratories, and industry partners who are involved in research projects. It's probably the largest consortium of researchers involved in water treatment research ever.
And the headquarters is at Lawrence Berkeley in Northern California?
That's right.
Okay, so as I said, there are no silver bullets to climate change, but when you bring people in who don't have a lot of context and you say, hey, water is going to be one of the biggest problems that we deal with in a changing climate, in a world impacted by climate change, the average person will say, well, hey, why can't we use desalination on the ocean? Isn't that the answer?
Oh, it's a wonderful answer. It's a great answer.
So tell me about the state of that today.
Sure. Well, for starters, ocean desalination, there are some countries like Israel and the Kingdom of Saudi Arabia where the majority of their water supply is from desalinated ocean water. It's a now 60-year-old, I would not call it mature because it continues to improve, but it's a very stable and reliable source of water. And one of the things, Cody, about ocean desalination is that that water supply is invariant to climate change. That is to say, no matter how hot it will get, we will always have ocean water, which means you will always be able to extract fresh water from those ocean supplies. Now, one of the principal challenges of ocean water is it's pretty salty. Ocean water has 3.5 grams of salt per liter. It's very salty. The challenge is figuring out how to pull those salt ions out, and it takes a lot of energy. So seawater is salty, and it literally, the chemical energy required to physically separate those salt ions from the water is pretty intense. And so one of the concerns people have had about desalination is that, wow, if we suddenly supply the world's water supply with desalinated water, we're going to have a huge increase in energy usage. And so that's why at NAWI, we tend to point people to the fact that there are many other places around the world away from the coast where you can find water that's not nearly as salty as seawater. And if it's not as salty as seawater, it doesn't take as much energy to desalinate it. The other challenge about ocean desalination is that we live on a planet with gravity and water is heavy. And if you have the water at sea level, simply lifting, even after you desalinate that water, lifting it up into the communities where it's needed can take an enormous amount of energy. My wife and I live at 1,140 feet elevation in the San Francisco Bay Area. And the energy needed just to lift the drinking water up to our house is about the same amount of energy used if it was desalinated water. So that's one of the challenges.
And talking about energy use, you mentioned Kingdom of Saudi Arabia and Israel are two places where this technology is widely deployed. Kingdom of Saudi Arabia obviously has lots of domestic energy in its oil and gas capacity. Not necessarily the best solution from a long-term climate change perspective, but it probably solves their near-term water needs. Israel, however, does not have those natural resources. Do you know what energy sources Israel is using to power its current desalination footprint?
So Israel does have some oil and gas, but Israel's energy sector is much more diversified with a much greater amount of renewables. Interestingly enough, Cody, even though Saudi Arabia is got an enormous reserve of oil and gas, it turns out that today's photovoltaics costs are so low that many of the new projects that they're contemplating in the Middle East are actually going to be desalination projects driven by photovoltaics, by renewable energy. And that's one of the really interesting things about renewable energy in combination with desalination, is that one of the challenges of renewable energy is that, especially photovoltaics, they come on when the sun shines, and you often get a huge amount of electricity, not necessarily when you need the energy. So one of the really interesting opportunities for desalination is combining desalination with renewable energy supply. You could produce a lot of water during those sunny days and store that water, almost like a battery. You could store that energy in the form of water and then use that water and turn off the desal plant when you don't have the renewable energy.
One of the other challenges is around the brackish waste that comes out of these plants, right? And what to do with it, as I understand it. What are the worst case scenarios there? And what are some of the solutions that seem to be working well in that regard?
So as you rightly pointed out, Cody, when you desalinate water, you basically split the seawater into two equal volumes. One, salt-free water that's pure, and the other, a liquid that now has twice the salinity of seawater, and we call that brine. And one of the common challenges with brine is not only is it super salty, but it also is denser than seawater. So it's like cherry syrup. And if you just put that brine and poured it out in one location, it would fall to the ocean floor and smother the life around it. So in the United States and in places like Florida and California, the regulations require that that brine be diluted enormously, factors of 100 to 1,000 to 1, so that by the time it comes back into the ocean, it doesn't have the potential to sink to the bottom. It's fully mixed. And there's a big ocean. So if you mix the brine completely, you can safely and successfully return it to the environment without any environmental consequences. But that's if you've got a nice convenient ocean in your backyard. When you think of desalination away from the coast, the disposal of brine becomes the dominant problem. In fact, it's really the Achilles heel of desalination inland in these non-ocean applications. And in that case, the only thing to do with brine is either to drill a hole and put it down a well, or literally truck it somewhere. It's enormously expensive. So one of the key areas of innovation we're focusing on at NAWI is taking desalination technologies all the way to the end, what's called zero liquid discharge, extracting every last drop of water from that seawater source and leaving behind just dry salts. And if you leave behind dry salts, there are two things. One is they're much easier to handle. They're much smaller in volume. And in fact, water is the universal solvent. So practically the entire periodic table is in water in some form. So you can actually take these residual salts and you can transform them into valuable chemicals. You can even extract valuable metals from some types of brines.
And forgive the maybe silly question, but back to your solution of if you are near the ocean, you have to dilute the brine to put it back into the ocean. Wouldn't that somewhat be then taking the water that you just extracted from the brine and putting it back into the brine to put it in the ocean? You've got to find water in order to combine it with the brine.
Yeah, so in fact, in Southern California, it's common that a desalination plant will just take their brine and dilute it with wastewater that's being injected back in the ocean, which is mostly fresh water. But as you rightly point out, Cody, why are we throwing this water away in the first place, especially wastewater? Why are we taking wastewater, municipal wastewater, and throwing it out in the ocean when in fact it's not very salty? And California, of course, is one of the states that's pioneering new regulations to allow for direct potable reuse, what's called DPR. And this would be a way of taking municipal and industrial wastewater, treating it to very, very high quality, and essentially putting it right back in the municipal water supply system. And desalination would be needed as a process step there too.
I listened to a podcast episode, I think it was on the New York Times, The Daily Show, maybe 6 or 9 months ago. And it was about Arizona and wanting to develop a desal plant in Mexico and actually pipe the water over the border. And there were all sorts of environmental concerns about the pipelines that needed to be built and the deserts that you would go through, and unfortunately, rare plant life and animal habitat that you'd have to go through to move the water. Do you see us in the United States, ultimately having to treat water as this rare of a resource that we're literally pipelining it over borders and across states?
I am not optimistic that any large-scale water transfer of desalinated water up and over mountains will ever be economical. And as I said, Cody, it's because water is heavy and we live on a planet with gravity. I haven't done the actual calculations, but just taking that water from the Sea of Cortez and bringing it up over the mountains and down into the Phoenix Metroplex would probably be more energy than the desalination process anyway, let alone the disruption to the national parks and the nature reserves that are on the way. So wholesale water transfers, that was a 20th century solution, Cody. And in fact, California, for those of our listeners who live in California, driving down I-5, you drive past these amazing canals, these aqueducts, which ferry water from California's relatively wet north to our dry south. That was all built from 30s, 40s, 50s, and 60s. And we are just not going to be able to have a 20th century mindset when it comes to solving climate change in the 21st century. So rather than think about big, massive infrastructure, we need to think smarter. We need to think in terms of small-scale distributed technologies that can allow us to reuse water over and over again. And that's really one of the themes of the NAWI program.
Great. Okay, so you've satiated my need to scratch the itch on why can't we just build these big plants by the coast. I explained many reasons why those are a challenge. So what is the 21st century to water, and what does it look like in your mind?
So the NAWI program, as we said, our 20th century technologies tended to be big and they tended to be centralized. And that made a lot of sense for building cities in a period of growth. But if we are moving into a realm of, as you said, Cody, hardening our infrastructure against the effects of climate change, we need to think about using water more locally and using it and reusing it over and over again. So in fact, one of the areas that NAWI is pioneering is small scale desal systems. So in other words, rather than building a big plant from scratch with decades of permitting and everything, can you make small package systems that you can literally bring salty or wastewater in at one end and produce clean water out the other end? I fancifully call this my water washing machine. I want to be able to make desalination systems down to essentially the appliance scale. And that means that most buildings in the world could essentially recycle and reuse most of their water. And there's some really interesting examples of this, Cody. I'm sure in your journeys, you've heard the quote, the future is already here. It's just not uniformly distributed. I don't know if you've heard that quote. But in fact, there are a couple lighthouse environments where you're seeing this 21st century approach to water. One of them is San Francisco. In San Francisco, they passed a building ordinance that if you're building a new building, 100,000 square feet or more, you may not flush your toilets with drinking water. You may not irrigate your landscaping with drinking water. You have to use recycled water from the building. And as a result, new buildings in San Francisco are being built and installed with small scale packaged reuse systems. And as a result, they have about 40% lower water footprint than the building otherwise would have. And so premise scale reuse is a really exciting frontier of being more water efficient. And in many respects, Cody, it's similar to our transition in the energy sector. We used to have power plants that were very large, custom built, took decades and cost a lot of money, and they burned fossil fuels. Today, we still have that fixed infrastructure, but we also have augmented it with distributed renewables in the form of solar panels and wind. Maybe we could do the same thing for water with centralized systems of the 20th century being supported by decentralized small systems across a city or across a county.
It does strike me as being parallel to the whole distributed energy solution, except that with water, I mean, I guess in the case of purifying it to the point of being drinkable, there's a heavy amount of regulation and public safety involved that many people would probably trust their utility or a central body to manage, but may not trust a local building manager to stay on top of it. How does that factor in? How do you see that playing out?
That's a great point, Cody, because one of the foundations of our safe and frankly, very high quality and frankly, very low cost water supplies that we enjoy today are based on a public health framework where we have regulatory agencies, hardworking men and women at the state level who ensure that all our public drinking water systems are operating safely and securely. And when you think about suddenly saying, well, now I'm going to have a water washing machine in the basement, like how's that thing going to work? This is a current frontier of research itself, Cody, is how do we make technologies so reliable that the regulatory community can be confident that when water is reused, it's reused safely. Now, remember, we're not using all the water for drinking. In fact, even in a house, only about 50% of the water is used for direct ingestion. And so one of the theses we've had at NAWI is that you don't need the same water quality for all applications. And in fact, drinking water is actually not the best quality water for different applications. Look at it this way. If you're going to clean clothes, you may actually want to have a certain low minerality so that the detergents work better. So that's a different flavor of water that's optimal for cleaning clothes. If you are bathing, one of the really interesting things about drinking water, Cody, is that because we have public drinking water systems, they have to keep a small amount of residual disinfectant, chemicals that keep the water from getting bacteria. Those residual disinfectants actually produce byproducts that can be hazardous to us. And so the EPA regulates disinfection byproducts. But if you were bathing, you didn't want to inhale all those volatile organics. Instead, you would probably want to bathe with water that had low residual disinfectant. So as we look at the house, rather than thinking about gray water, which is indistinct, uncolorful term.
It's also not a very appetizing term, is it?
Absolutely. Who wants to cook with gray water? I would rather cook with high quality water. And we think that we could turn the water system into a barista where if you were poaching trout tonight, you would choose a low minerality Sierra Nevada type water. Or if you were making bread tomorrow, you'd take a high minerality water from the Dolomites and you could actually dial in the chemistry. These aren't science fiction. We know how to do these things today. The trick is redesigning our centralized dependence on one water, drinking water, when we're using drinking water for a whole bunch of applications for which it's not necessary, including flushing toilets. There's no reason that we should use this precious drinking water to flush toilets.
And yet homes are built with one plumbing system today. I get the new building code in San Francisco, but retrofitting the existing residential footprint across the U.S. would also be an incredibly daunting task.
Much like retrofitting our cities and towns for centralized water supply was a daunting task to our great-grandparents. And it took about 50 years.
We can get into the conversation of can the U.S. do hard things? I sure hope we can.
We can, Cody, after we exhaust all other options, as Winston Churchill said.
All right, on the question of hard things, I saw a stat in a report I found on your website, which blew my mind, that said that 41% of water withdrawals in the U.S. today is for the thermoelectric power generation sector, in particular gas, coal, petroleum, and nuclear. I would have thought, the second biggest use of water is probably food and ag and or industrial, but I didn't even think of power generation. Explain that to me.
Well, they're not consuming it and making it go away. What they're doing is they're taking in cold water from a river, putting a bunch of waste heat in it and throwing it back in the river slightly warmer. So when you see the term thermoelectric water use, it's mostly they're just dumping excess heat from a combustion process into the water and throwing the water back. Now, that's not trivial. There are a whole host of environmental concerns with making sure that you have the water not too warm for the ecosystems. But Cody, one of the real challenges and one of the reasons why the U.S. Department of Energy first woke up to the idea that water was an issue was that about 10 years ago, during a series of droughts, you actually saw power plants curtailing their power generation because they literally didn't have enough water to cool and operate their systems. So, for example, there were blackouts in the southeastern United States and Georgia. And that was when the Department of Energy realized, oh my gosh, water and energy, they're critically linked. It's not just that we use energy to produce water, but we actually use water to produce energy, but we actually use a lot of energy to produce water itself. And so that idea that there is a water energy nexus and a connection was one of the things that drove the creation of the NAWI program.
And we've seen all these estimates coming out recently about the big technology hyperscalers and how much energy they're going to need over the next decade plus as we move into AI and all these really heavy compute processes. Do you expect that the water footprint of the compute industry is also going to be large such that the existing infrastructure hasn't planned for it?
Yes. In fact, we are seeing this already. The explosion of usage of data centers and just the CPU power demanded by AI is already causing electricity generators to file emergency applications for new power. And when you have new power, you also need cooling water for that. These data centers themselves often have to deal with an enormous amount of evaporative cooling, and that water is lost. So when you use water in a building, for example, for a cooling tower, you are using the evaporation of that water to carry off the heat. And so if we have a huge explosion in data centers, we're going to have a huge explosion in evaporative cooling needs, and we're going to need water for that.
So cooling for both the power gen and cooling for the actual data center itself, the fact that the machines themselves get hot.
One of the things we think about, it's not just that climate change is going to affect our natural water supplies. Climate change will also affect our water demand. How do we use water? So here's an example. People have been very excited at the potential of a hydrogen economy and using hydrogen as a clean resource for fuels. Well, hydrogen's made out of water, and you do need some water to make hydrogen. But most people don't realize that it's not just the primary water needed to create the hydrogen. The process, the electrolyzers that are used to split the water, they need to be cooled themselves. There's something like 5 times as much water needed for cooling in a hydrogen plant than the water supplied to split for hydrogen to begin with. And so as we think about these energy-intensive industries like data or hydrogen, we are absolutely going to have a huge water demand associated with that. And so when we look at decarbonizing our economy, it's quite possible that the water demand might go way up as a result of that.
Hey everyone, I'm Yin, a partner at MCJ Collective, here to take a quick minute to tell you about our MCJ membership community, which was born out of a collective thirst for peer-to-peer learning and doing that goes beyond just listening to the podcast. We started in 2019 and have grown to thousands of members globally. Each week, we're inspired by people who join with different backgrounds and points of view. What we all share is a deep curiosity to learn and a bias to action around ways to accelerate solutions to climate change. Some awesome initiatives have come out of the community. A number of founding teams have met, several nonprofits have been established, and a bunch of hiring has been done. Many early-stage investments have been made, as well as ongoing events and programming, like monthly Women in Climate meetups, idea jam sessions for early-stage founders, climate book club, art workshops, and more. Whether you've been in the climate space for a while or just embarking on your journey, Having a community to support you is important. If you want to learn more, head over to mcjcollective.com and click on the members tab at the top. Thanks, and enjoy the rest of the show.
Okay, and as we talked about, trying to pull it out of the ocean, probably not economically feasible for a number of reasons. Trying to recapture it from existing use, certainly something that we should be spending more time on. And then there's a big whole topic that we haven't talked about, which is stormwater. And how do we take the water that falls from the sky and actually not just run it through concrete down to the ocean, but actually do something with it? That is huge civil engineering work that needs to get done, if I'm not mistaken.
It is. It's both huge, but it's such a sweet opportunity. Los Angeles is a great example. Los Angeles had this dry valley. We paved it over with roads and buildings, et cetera. And we took the LA River and these other rivers and we made a hard conduit and we shot that water out to the ocean as soon as possible. What a mistake. So actually, Los Angeles is also a great pioneer in this area. There is a recent, I don't know if it was a proposition, but a measure called Measure W. And what it did is it encouraged the creation of porous infrastructure. So if you were building a new building, say, Cody, they would map your roof, which is impermeable, and they'd say you have a tax based on the impermeable area in your property. However, if you go ahead and put permeable pavers and ways of diverting that wastewater back into the ground, we actually give you a credit. And so what they've done is they've given an economic signal into the building community of Los Angeles to think about being a sponge. Los Angeles could be an enormous sponge city by building this infrastructure from porous permeable pavers to gutters that naturally treat water. There's some really interesting technology, Cody. If you've been to a recent department store or a Target parking lot, you'll notice that instead of just regular curbs, they have these deep little valleys with it looks like a bunch of weeds growing and you don't pay it much mind. What that is a natural water treatment plant. The water sheds off the pavement, goes into these little gullies, and the plants and the gravel in the gullies actually treat the water and then allow the water to seep back to the groundwater. So we could build cities and re-engineer cities to be much more in equilibrium with the groundwater.
And is the goal there to replenish groundwater, or is the goal there to actually funnel water to our water treatment facilities for immediate use?
Well, in places like Los Angeles still draws a lot of its primary water supply from groundwater. So the idea would be you're balancing the load. As you may be pulling water out of the ground, you have other infrastructure that makes sure that water returns to the ground.
Okay, so all incredibly helpful context, setting the stage of our water challenges and opportunities ahead of us. How does your work factor in? What are the types of projects that NAWI is working on? Where should we expect to see them in the future? And at what technology readiness level are you tending to engage?
Great question. So I'd say three key areas that NAWI is focusing on. The first one, as I said, is ultra high recovery desalination. So how can we extract every last drop of water from a source and leave behind just dry salts? There are enormous benefits, but you can imagine just from an energy standpoint and a chemistry standpoint, extracting those last few droplets is enormously energy intensive with today's technologies. So we're working on some really clever technologies involving electric fields and membranes that can actually allow that to happen at a much lower energy. So reducing the cost of high recovery desalination is one area. Another area where we're focusing is the recovery of valuable materials from wastewater. So as you know, we throw away this wastewater. It's got a lot of organic matter in it. That could actually be processed and turned into fuel. And there are many, even in the United States, there are a number of wastewater treatment plants that produce energy because they take this wastewater, they put it in a reactor, and it produces methane. And they can burn the methane and generate electricity.
And this is both municipal and industrial wastewater?
Yeah. But even beyond just generating energy, the fact is that there are places where wastewater can be very abundant in certain precious metals. Magnesium, for example, which is a very attractive lightweight alloy, is presently only made in China and Russia with some of the most dirty and carbon-intensive manufacturing technologies there are. It turns out we could extract that magnesium from natural and industrial waste brines and have a lightweight alloy to go with aluminum and vastly reduce the weight of our automobiles, for example. There are precious metals that we mine in remote parts of the world. Those could be extracted from waste. And then, of course, there are building materials like cement and concrete, et cetera. Those base chemicals could be harvested. Then the final area that NAWI is focused in, as I said, presently, as you mentioned earlier, when you think about small-scale desalination and water reuse, you get into the question of, is it safe? Is it reliable? Can I know that the water that this device is producing is truly going to be good for me? And so that is actually an area of very important research, is can we make the technologies very reliable? Can we make the software that runs those technologies so simple and easy to use that the system will always report that its status? Can we also lower the cost by manufacturing efficiencies? Can we make things over and over again in a way that we can punch out and stamp out these little water washing machines at a cost that would make it easy, rather than spending millions of dollars digging trenches and burying pipes like the 20th century mindset? Can we install in the basement little devices that will basically reprocess the water? Imagine if our apartment buildings had kidneys. In other words, they would be taking the wastewater and reprocessing it like your kidney.
That's a very helpful analogy. So then thinking through the pathway for these ideas to find their way to deployment, when they come through NAWI, where do they tend to end up from a commercial readiness perspective? And what is the handoff or the pathway for them to find customers? You have 100 plus different organizations working in water that are, I think, partnered with you at NAWI, in addition to universities and the national labs that we discussed. What does the ongoing pathway look like?
So one of the things about water treatment research is that stuff in the laboratory is interesting, but it gets real when you actually bring technology out into an operating environment. So one of the key areas of focus for us this year is we've launched nearly a dozen pilot systems, and many of them are trailer-based systems going out into operational environments. We have one that's going to visit 5 different localities in the state of California. They're going to Cambria, California, where they have a RO system where they're having trouble disposing of the brine.
What's the RO system?
Reverse osmosis, excuse me. One of the main methods of desalination is reverse osmosis. So the city of Cambria has this reverse osmosis system, but they have a challenge of disposing of the brine. So this trailer is going to come up and show them that we can squeeze literally every last drop of water out of that brine and vastly reduce the cost of brine disposal. That same trailer is going to go to a greenhouse in Ventura County. It's going to go to an oil and gas production facility where they are currently challenged to dispose of the produced water. And so showing that these technologies can actually work in realistic environments. That is the game for NAWI, and we're going to be doing even more of that in NAWI 2.0, the second 5 years of our program.
Where do you think the U.S. is today on the water innovation front, particularly thinking back to where we have come from a clean energy perspective? If you see the path that clean energy has undergone in the last 2 decades, where are we in the water innovation cycle?
Unfortunately, the United States bought the cheap seats when it came to the water amphitheater. We're not in the frontier. Other places in the world that have had a much more acute water supply crisis have actually really paved the way. One is the city-state of Singapore, where their only natural watershed is in Malaysia, in another country. And so they have been very sensitive to the idea that they need to have water resilience because they literally don't control their water supply. I mentioned Israel, and many of the countries in the Middle East are places where you're seeing a much larger fraction of water being produced from desalination. And Australia is another place where you see some really innovative practices. That being said, just because we weren't first doesn't mean that the United States can't make some very important advances that will help the rest of the world. I think the idea of small-scale desal is largely something that we're pioneering in the United States. And this idea of water reuse is something that is very attractive in the United States, especially where we want to continue economic expansion, where we want to continue to grow our cities. For example, Phoenix, there are places in the greater Phoenix metroplex where they literally have a moratorium on new houses because you can't supply the water. So could we, in fact, unlock economic growth by essentially making our infrastructure more water resilient and more water savings?
One thing I've learned about climate is obviously a big challenge with climate change, in particular with greenhouse gas emissions, is the lack of accounting for the externality of them when it comes to businesses and their continual creation of emissions. Today in the US, Europe has done a lot more on this, but in the US, emissions are a voluntary thing that companies can choose to remove, but they're not required to. You're seeing more and more pressure that is causing companies to be cognizant of it and manage against it. And California has recently passed legislation requiring companies to account for it. What are the economics of water today? Are companies paying for their water use? Are they responsible for how much water they consume in their operations? Is it something they have to actively consider in managing the forecasts of their business?
When I talk to business leaders and corporate leaders, it's commonly the case that for the most part, the cost of water is not the concern. We in the United States actually have shockingly cheap water. And we have shockingly cheap water partly because our great-grandparents invested in these systems that delivered reliable water to our agricultural sector and to our cities. Where I see the real concern is in the industrial sector. They realize that water and water use is a critical part of their environmental sustainability goals. And they will be judged not on whether their prices go up because water is more expensive. They will be judged by how their water demand is impinging on the rest of the community. And interestingly, one industry that surprised me by being very forward-leaning on water treatment is the mining sector. And speaking to leaders in the mining sector, they've determined that they will not have social license to operate a new mine unless they are stewards for that property forever. That means to say they need to be engineering the mining and extraction process and the closure and site rehabilitation process in a way that is permanent, not just walking away. And so this need for making sure that you have social license to operate, this is what's driving a number of industries to really push forward in water reuse. Even industry leaders like Amazon and Pepsi, they're rich. They can afford more expensive water. That's not the point. The point is they realize that if they don't show up with a more progressive approach to wise water use, they could face a real pushback with brand harm and negative repercussions. And so I really credit the industrial sector as recognizing that this is not simply a cost of doing business, it's a values associated with doing business.
In the US, we have the Department of Energy, as you've pointed out. They are very much responsible for setting the roadmap of where the United States is going from an energy perspective. They are defining the programs, the funding mechanisms, and in many cases, identifying the types of technologies that the US needs to continue to pursue and create. There isn't really an analog from a water perspective.
I wondered whether you were going to say this. Where's the Department of Water?
The EPA is a defensive mechanism helping to avoid
The EPA is a regulatory agency.
environmental calamity, but it's not setting the roadmap for where we go per se.
No, the United States is unusual in its federal policy making with respect to water. And many other countries actually have water management as a resource as part of their Department of Natural Resources or their environmental departments. But the United States, we split it up really weirdly, Cody. Think about it. If you have water west of the Mississippi, that's the U.S. Bureau of Reclamation. If water falls from the sky, that is NOAA. But if you put a boat on it, it's a different part of NOAA. If you look at it from space, it's NASA. If you put stuff in it, it's the EPA. It's crazy. It's crazy. So the federal architecture for bringing forward coherent water policy is harder in the United States. Now, that being said, there's also some really great trends on the horizon is that water is a big unifier. And in fact, we at the NAWI and the Department of Energy are in active collaboration with the U.S. Bureau of Reclamation and the Department of Interior and with the EPA, because we recognize that DOE's strength is bringing forward new technologies. EPA's strength is defining what those technologies need to do from a regulatory and public health standpoint. And other partners, such as Department of Interior and Commerce and even Agriculture, can give us a sense for how the water is best used in the industries and settings that they regulate. And so as long as we work together, Cody, these different federal agencies can really be successful. But it is unusual that we are so scattered across many different federal agencies.
And I know very early in your career, you had a position at the DoD. To what extent is maintaining access to a water supply more and more of a national security conversation at the DoD?
The Department of Defense actually is a remarkably progressive agency in many respects. They're very progressive when it comes to new technology. They're also very progressive in looking at the effects of climate change. They were some of the earliest federal agencies that were insisting that we have more consistent policy in this regard. So the Department of Defense cares about water for several reasons. For starters, soldiers happen to need water. Okay, so if we are going to have a military force, we need to make sure that water is one of the things that can always support our warfighters. It turns out, Cody, in Iraq, many of the casualties were not the forward-fronting fighters. They were the men and women driving trucks full of crates of water. And so the logistics associated with supporting the warfighter really got the DoD concerned about, can we do a better job of making devices that can produce water where the soldier needs it? So that's one area. The other thing is that the Department of Defense is long aware that water and water conflicts can drive instability, can drive the things that end up leading to a crisis. And so there too, understanding how to make the Department of Defense's infrastructure more resilient to climate change and water, as well as understanding where water is going to be an impinging point and a source of conflict, are two things that I think I really give them credit for. The U.S. Department of State feels the same way. The U.S. Department of State operates, of course, embassies around the world. They have to make those embassies very resilient. You never know when things are going to get problematic in your host country. So there too is an interesting place where water resilience and even energy resilience are valued. And so I'm optimistic that some of the leadership from those agencies as practitioners can really help guide us to a more energy sustainable set of technologies.
It would also seem to me that the work you're doing on distributed technologies for water would be of high interest to an organization like the Department of Defense that has military bases all over the world and maybe doesn't have large geographic footprints in those geographies. Can you share, just walk us through your background? How did you end up in the place where you are today?
Well, so as they say, careers make sense, but only in the rearview mirror. I am presently, as you know, the executive director of NAWI. But before that, I was actually the CEO of a water technology company called Pax Water. We worked on making municipal water distribution systems more safe and improving the water quality for citizens. And before that, ironically enough, I had previous startup in optics manufacturing. And before that, I was an operating scientist. And I often actually written extensively on the subject of career development for scientists and engineers, Cody. I don't know if you know that about me, but I've written 2 books on that subject.
What are they called?
The latest one is called Put Your Science to Work, and it's a practical career guide for scientists and engineers. And one of the things I emphasize, especially to early career scientists and engineers who spent years in academia, is to appreciate that academia is a wonderful place, but there are so many exciting problems for smart people to work on. And as you know, Cody, in your journey of 500 plus episodes, we have never needed more clever, dedicated technical people than we do now in this climate challenge. And so the opportunities for smart people to make a difference in a wide variety of career fields, not just in research, but in practical environments, has never been greater. And so I always encourage early career scientists and engineers to think outside the box of academia and think about places where their combination of their interests and their passions can be put to good use.
Great. And going from also a scientist with a PhD and an MBA, seems like you are well credentialed for this work you're doing now, which is to identify future innovations, but also try to help them find pathways to eventual deployment and commercialization.
Yeah. And I would say that this is a very important thing I emphasize to all our researchers, is that even though the reward mechanisms for academia and research tend to be in the form of publications and that sort of thing, the work you do is essentially meaningless if it doesn't end up somehow affecting our built world and what we're doing. And so I always encourage our scientists and engineering teams. In fact, every one of NAWI's research projects has industrial partners. That's not the case for a lot of research. For example, funded by the National Science Foundation, they often focus on scholarship and research articles, which are wonderful, which form a nice foundation. But the vector of innovation, Cody, is people. It's not publications, it's not patents. It's people choosing to go out and take a new technology and make something of it. And so I always emphasize that you can never learn enough about the practical environment in which your technology is operating. And the more that you spend out in those practical environments, the better insights you get, frankly, to do better science.
It reminds me of, there's a great book about Pixar called Creativity Inc. And they talk a lot about when they are about to write a storyline for one of their films, they go out and do the research, which is, if it's Finding Nemo, they go scuba diving, or if it
was Cars, they drive across the country. Remember they did that?
Exactly. Yeah, for the movie Cars, they drove Route 66. So it's just taking in the actual environment in which you are building product. It's the age-old advice to go talk to your customers. But in your case, learning about the way the existing water system works and the way the existing treatment plants work, I suppose. Lastly, any final thoughts?
I guess you and I started this episode talking about the number of interviews you've had and just the complexity of the issue. And I would simply say that when I started back at the Lawrence Berkeley Lab, I too was full of questions and concerns. And in the last 7 years, not just the research we're doing at NAWI, but also the breadth of research that's going on in the Department of Energy, I am more and more optimistic about us arriving at this challenge. Not to say that the work is done, or that the work will be easy, but I have seen more and more indications that we are a clever community of people And there are ways in which we can engineer things to mitigate this effect that we're having in the world that we live in. And so I guess I would say I remain an optimist. And I think one of the things about these challenges is it's also fun. It's fun to work on the frontier and to try to make a change and to try to re-engineer something. So that's the passion that we have at NAWI, and we'll keep at it for the next 5 years.
Well, I feel like my generation, maybe my parents grew up taking energy for granted. And I think we've all realized you can't take energy for granted. There's so much complexity and it's so important and it has so many areas in our lives that matter. And I feel like water is this next big problem that many people are starting to realize we have really taken it for granted, at least here in the United States. And that can't continue to be the case. So thank you for the work that you are doing and the work that your team is doing. And I can't wait to see many of these innovations find their way to all of us.
No worries, Cody. Thank you for the opportunity to speak to you today. Anybody can learn about the NAWI program at www.nawihub.org, NAWIHUB.org. Every one of our research projects has a single one-pager profiling. So if you really want to get your desal nerd on, you can go page through all our research projects and even meet with some of our researchers.
Dr. Peter Fiske, thank you very much.
Thank you, Cody. Take care.
Thanks again for joining us on the My Climate Journey podcast.
At MCJ Collective, we're all about powering collective innovation for climate solutions by breaking down silos and unleashing problem-solving capacity.
If you'd like to learn more about MCJ Collective, visit us at mcjcollective.com. And if you have a guest suggestion, let us know that via Twitter at MCJPod.
For weekly climate op-eds, jobs, community events, and investment announcements from our MCJ venture funds, be sure to subscribe to our newsletter on our website.
Thanks, and see you next episode.